Then I think we should try the calculation once again. Okay. Another time let me do. Let me do it once again. Magnitude part is correct. It's coming with everyone. Uh, 4. It's correct. 53 into 10 to the power minus 37. That means. Oh no. 36. I'm also getting 36. I don't know how. Okay, try the calculation once again. I mean the process is correct. Okay, this is the process. Maybe there is some problem with the calculation. Okay. It may be 36 then. It is incorrect in the book. Let me see if there is any numerical of this type in the any other part, so that we can compare the answer. No, it is not there. Okay, Shravan, others, you just repeat the calculation one more time at home.
Okay, so
Method is this one. Okay, so I won't be waiting for anyone. Now a very important property that I will be using, that I will be discussing. That's called the boundary conditions on electric field vector and the electric displacement vector. Okay.
sir.
Yeah.
So can you explain that previous the unit, sir?
Unit.
Yes, sir. That you told that it
Oh,
was coulomb
acha.
meter square, but you divided
Yeah.
by.
What is P? Remember, P was what? Dipole moment per unit volume. Okay. What is dipole moment? Charge into length. So coulomb meter. I divided this by meter cube. So what was the unit of polarizability? Polarization. Coulomb meter square. Okay. Did you get it, others?
So coulomb
Yes,
per
sir.
meter square.
Yeah.
Coulomb per
Sorry,
meter
coulomb
square, sir.
per meter square. Sorry. Yeah. Coulomb meter minus 2. Yeah.
That time you told the coulomb meter, no? That's why I got confused, sir.
No. It is for this one. And that I told for P by N.
Okay, sir.
Okay. P by N and P are different quantities. No? So what boundary are we talking about? That is the question. Why boundary or also setting? Suppose we have two medium. Like in light, this is called one rarer, one denser. And there was something called interface, isn't it? That is actually the boundary. Something that separates the two medium. Say it is medium 1, it is medium 2. Having studied uh, electric field and this displacement vector, I mean the properties of dielectric medium, we can expect that phenomena to occur from one medium to another, isn't it? We can have situation like this when there are two media and there is a boundary. So how would these things change across the boundaries? That is what we are curious to know. Okay, and this thing is very, 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 very important because many numerical problems come from this part. Anywhere, competitive exam, university exam, and it is also very interesting. So you will have a scope to increase your concept. So let us draw two media, say 1 and 2. Say it is medium 1 and above is medium. You can draw a straight line as well, but it's a general thing because you may think that why always we have to draw a straight line. It's not that the boundary always have to be straight line. It's not always like a wall. I mean a straight wall kind of that. Anyways, so S1, S2 is the surface that is separating. Okay, it may be a three-dimensional thing. We are viewing it from above. Think it that way. Very so let us assume that there is a free charge density sigma on the surface. Okay, surface has some free charge. So free charge density on the surface S1, S2. Let me call that sigma. I hope by this time it is clear. What do you mean by free charge and bound charge? Okay. So what we'll do, we'll have to in fact apply Gauss's law here. Okay, Gauss law, and we know that we can draw Gauss surfaces. So we'll draw a Gauss surface, which is we'll draw a Gaussian pillbox. What is a Gaussian pillbox? When we tried to find the electric field due to an infinitely plane conducting surface, what we used to draw? We used to draw a pillbox kind of thing. What is a pillbox? It is a shape whose cross section is much large compared to the height. Okay, like those cans which contain that boot polish. Okay, area is big, but the thickness is the depth of the box is very small compared to that. If you don't remember this thing, you can just this was in class 12 as well. This how to draw these Gaussian surfaces. Okay, we will draw it. Say at the point O. Because if you want to apply Gauss law, you have to have a surface. Okay, we have to choose it. So this area is suppose delta S and the height is negligible. Very small. Height is very small. Why are we taking the height very small? So that we can stay very close to the boundary itself. Okay, so this is the boundary. We can stay very close to the boundary. That is, as this height tends to 0, the flat surfaces are as if they are on the boundary itself. Did you understand why are we choosing this surface and why is it drawn such that the height is very small?
Once more, sir.
First we are choosing a point on the boundary. Then we are drawing a Gaussian surface which looks like it's like a cylinder, but its area of cross section is very large and its height is very small. The reason we are taking the height very small so that these two flat surfaces, this is one flat surface, another flat surface, so that these two surfaces are very close to the boundary. Okay, we are not moving far away from the boundary.
Yes, sir.
I need to complete the diagram because whenever you are drawing a surface, surfaces are incomplete without unit vector. So suppose this is the unit vector in one cap for this surface, n2 cap for this surface. Unit vectors, when you denote any surface, they will always be outward normal, okay? Normal facing away from the surface. This media say has permittivity epsilon 2, this one has permittivity epsilon 1. So now let us apply Gauss law. So by Gauss law of dielectrics, okay, definitely what we can say, d dot nds is equal to what? Total free charge enclosed, isn't it? Free charge, QF. In the last class we got this thing, no? QF. Now what did we assume? We assume that the charge density is sigma. What is the surface area? Delta S. See if you got it or not, this thing.
Yes, sir.
That is another reason why we are choosing this side very small, so that virtually these two flat surfaces are on the boundary. Then only I can apply this thing because sigma is on the boundary, not away from that. So you can see that there are two surfaces, this one and this one, and this height being very small, negligibly small, we need not to consider that integral. That integral would eventually cancel out because the directions would be such. Okay, you need not to consider this. You may think like this, that the height is negligibly small, so the only surface we want to bother is this. Okay, so d2 dot n2 cap delta s, that is this surface, is d1 dot n1 cap delta s, that is equals to sigma delta s. Because there are two surfaces, so two results will come. So you can see that delta 1 dot delta 2 minus delta 1 dot n cap is equal to sigma. Where did the minus sign come? See properly in the figure, n1 and n2 are oppositely directed, isn't it? One is pointing upwards, another is pointing downwards. And both the surface area are equal, so their magnitude will also be equal. So we are assuming that n1 cap equal to minus n2 cap equal to say n. Okay. Think it this way. Let me redraw the picture. The boundary the surface, and I am drawing this pillbox with some height, else it won't look good. Okay, I mean I'm not drawing this side too small because we have to understand. So we have N2 cap here. Epsilon 2 is the permittivity in that medium. This medium 2, medium 1. Okay, now see one thing. Suppose your electric displacement vector is making an angle θ1 with this surface, and this one is making an angle say θ2 with the upper surface. It may happen so. Did you understand this thing? Please respond if you
Yes,
can't.
sir.
Okay. So see, d2 dot n. What does it say? Okay, both are in. Magnitude is same. So d2 dot this thing. Can I write this one as? Okay, let me write this equation like this. Now can I write d2 dot this vector equal to d2 cos θ2? Just see if I can write it like this or not. Same thing, projection. A vector, B vector, theta. So this portion is how much? A dot B is equal to how much? AB cos theta. And magnitude of n is 1 because it's a unit vector. Simple dot product. Yes. So these components are called the normal component. Why? Because d cos theta is along this direction, normal to the boundary. So the normal components of d, they are not equal. This one is in medium 2, this one is in medium 1. They are not equal, they are different. So what we say that these components are discontinuous across the boundary what is the amount of discontinuity? It is discontinuous by the surface charge density. That is the conclusion. That is, if you move from one medium to another, the normal components of the electric displacement vector would be discontinuous by what amount? By the surface charge density. Clear?
Yes, so
Now tell me, when will they be continuous? Under what condition these two components will be continuous? What do you think? Under what circumstances will they be continuous?
when sigma is 0, sir.
Very good. Yeah, when there are no free surface charges. Okay. So they are continuous if sigma equal to 0. So whenever we face a numerical problem, first we have to see whether uh, there is some free surface charge density or not. If not, then simply if sigma is 0, then d2 cos theta 2 equal to d1 cos theta 1. They are continuous. Sometimes it is written like this: d2n equal to d1n. N stands for the normal component. Okay, so that is how this change occurs across the boundary. Okay, there is a slight confusion whether to use polarizability or not. See, in these cases, polarization has not been mentioned. Okay, so we can, what is otherwise? Otherwise, we write that D is equal to this thing, isn't it? Remember, this thing will come into play only when there is some polarization, isn't it? That means only when you are putting the dielectric medium into what? In an electrostatic field. Otherwise, P is 0. So you can see in this treatment that we just did, there is no mention of that polarization. So in this case, I mean, is in doing these boundary conditions, P is 0. Oh, sorry. Sorry, I got confused with other thing. Extremely sorry. Got confused with another thing. So sorry. Oh, yeah, this is the thing. I was thinking of that previous problem. Okay. So what did we get ultimately? So we got D equal to epsilon E, isn't it? Forget this thing. It's totally wrong. This thing we got, remember?
Yes, sir.
So what if I want to see whether the normal component of electric field changes or not across the boundary? That is, what is this condition in terms of E? So what we got? We just got D2 cos theta 2 minus D1 cos theta 1 equals sigma. So uh, this can be again written like this. Now D is equals to E into E. Sorry, epsilon into E. So it would be epsilon 2 E2 dot n cap. This would be epsilon 1 E1 dot n cap. This is how the condition will look like for electric field. Now, how to remember whether many people get confused whether the relation is this or whether it is this. Okay, they get confused, especially in these kind of problems. Okay, one thing you can remember, what is the spelling? How do we spell D? How do we pronounce D? How do we pronounce? Isn't it? This is the pronunciation of D.
Yes, sir.
So D is equal to 2E. One E for epsilon, another E for. That is how you can remember this thing. If you remember this derivation, then you will never forget that D is equal to epsilon into E or E is equal to epsilon into D. That confusion will never arise. But if you forget in the exam, then remember this trick. that D is equal to epsilon into E. Now what about the tangential component? That is, we got the component which was normal to the surface. What about the component which is parallel to the surface? Again, let me draw the surface. This two. Now, in order to draw the, to get the component parallel to the surface, we'll do one thing. We'll draw the Gaussian pillbox as a rectangle now. We'll draw a rectangle. A, B, C, D. So length definitely AD equal to BC. Say it is delta L, and the height is delta H, which is tending to 0. That is negligibly small. Why? You can see this is not a straight line, isn't it? The surface is not always necessarily a straight line. It can be like this, the boundary. So how can I draw something parallel to it? How can this be parallel? Only when, if this thing lies on this surface, then I can say, yeah, this line is parallel to this line. So we are taking this height very, very small, so that AC, AD and BC as if they are on the surface of the boundary. Okay. So again, this is medium 2, which has permittivity epsilon 2. Medium 1 has permittivity epsilon 1. And this is the electric vector. Say this is the electric vector E1, making an angle theta 1 with the normal to the surface. This is E2, making an angle theta 2 with the normal of the surface. And this point is O, where I am drawing the surface. Okay. So for electrostatic field, I think you remember this.
Yes, sir.
It's a conservative force. If so, then I can, then it is true for any surface. So I can do this thing. It is 0, then it is 0 for any surface. If we apply the theorem, Stokes theorem, what I can convert? Surface integral to, I can convert it to a line integral, say L, or a contour integral, whatever you'd like to call it, E dot dl. So this thing is 0. So if I expand this, what I will get? I will get C, E2 is in the second medium, dot, what is the length? BC. But since this is a vector, you have to keep track of the direction. So left to right. So it is, say, this, plus E1. What is the length here? It is also delta L, but it would be minus. Why? Because see, the direction is opposite to the above one. That is equal to 0. Why are we bothering the direction? Because the integration is on the line. Okay, it's also called the contour integration. CONTOUR. You studied in your higher semesters, where you have to take care of the direction as well. Okay. So now, if say tau cap is the unit vector along the tangent of the interface, that is, which tells you the direction which is parallel to the interface. Okay, n cap was normal to the interface and tau is parallel to the interface. Then what I can say, then this can be replaced by tau cap delta L, and this can be replaced by tau cap delta L as well. So you can see that E2 dot tau cap is equals to E1 dot tau cap, and this would be E2 sin theta, and 2 this would be E1 sin theta 1. Why? Because if you have a vector like this makes an angle theta with one direction, the direction which it is making the angle, that would be the cos component, another one would be the sin component. It is making angle with the, here it is making angle with the normal, so along that direction it will have its cos component. And what is the direction perpendicular to the normal? The tangent. Tangent means this direction, so in that direction its component would be sine of that. Got it? So
Yes, so
the tangential component of electric field vector are continuous across the boundary, irrespective of the fact whether there is any free charge density or not. It would always be continuous.
so can
This is
express the
one.
minus del also.
This one. This one.
Minus del L also.
Yeah, why is it minus? That you are asking.
Yes, sir.
Yeah, that is the reason. What is tau? What you have to consider now? You have to consider the direction which is parallel to the interface. That is either this or this direction. Previously, what we are doing, we were taking the direction which was parallel, normal to the interface. That is 90 degree, either up or down. Okay, so see, when you are doing the integration in this direction, say this direction is tau cap, then this direction will be opposite to this one, isn't it? This direction is opposite to this direction, so it is minus tau cap. Right to left, left to right. Like in the previous case, upward direction n cap was positive, downward direction n cap was negative. Got it?
So but here we have only one line also, like parallel line.
Yeah, but we are assuming that this height is very small, but it is there. Actually, yeah, you're right, there should be one line, but we have to apply this theorem, this formula, sorry, this integration. This integration is on a closed surface, closed contour. So in order to make this one line into a closed surface, what I am doing, I am drawing it like this. I am making a very small height, then I am making like this. Okay, so as if it is one line only, this height is nearly tending to 0.
Okay, so
Because this integration means it would be in any closed path, clockwise, anti-clockwise, any direction. So I can't just integrate it over a line. Again, I have to integrate over a line because else I will move far away from the surface. So in order to take care of both the conditions, I am doing what? I am making a surface, but which is very, very close to the boundary. You can call this one negative, this one positive. Same thing. At the end of the day, result would be same. So this you can write it like this: 2t equal to 1t. T stands for the tangential component. So we got important results. One is what? d1 cos d2 cos theta 2 equal to d1 cos theta 1. Obviously, when sigma is 0, this can be written as epsilon 2 e2 cos theta 2. This is condition 1. Just now we got condition 2. Why not divide them? Because few terms look similar. So if we divide, what we would get? E2, E2, E1, E1 will get cancelled. So we'd get E2, sorry, epsilon 2 cot theta 2 plus 3 epsilon 1 theta 1. So tan theta 1 by tan theta 2 equals epsilon 1 by epsilon 2. When sigma is 0, no surface charge density is there. This is called the law of reflection of electric field at a boundary free of charges. Okay, so see, we got another result. By Snell's law also you can write it like this, isn't it? Snell's law also has something like this, na? mu1 sin theta 1 equal to mu2 sin theta 2. Then take the ratio, sin theta 1 by sin theta 2 would be equal to something.
Yes, sir.
Okay, so quickly let us do a numerical problem of this with this application. Which one will we do? It's very interesting. Yeah, got one. So the question goes like this. Suppose x equal to 0 represents the interface of a dielectric medium and vacuum. So suppose below I have dielectric medium, above is vacuum, or the other way around. The region 1, which is represented by x less than equal to 0, is occupied by a medium of dielectric constant (2.5), while region 2 represented by x greater than equal to 0 represents vacuum. If d1 equals 12 I cap minus 10 j cap sorry, plus 4 k cap coulomb per meter square, find d2 vector and theta 2, which is the angle made by T2 with the normal to the interface. Copy the question. When you're done, tell me. Then we'll solve. Copy it.
Yes, so
Fine. Try to understand the picture. X equal to 0. Suppose I'm taking the normal Cartesian coordinate system. So this is x equal to 0. That's the boundary. This above surface is what? This represents x greater than equal to 0. Below is this. So this is my region 1. This is my region 2. So region 2 is vacuum. Region 1 is a dielectric medium. Okay. So since region 2 is vacuum, this permittivity is epsilon naught. What is the dielectric constant of the material in region 1? 2.5. So try to remember the dielectric constant is what? Epsilon by epsilon 0. That is equals to 2.5. So what would be the permittivity of this medium? 2.5 times that of vacuum. Okay.
so
Is my picture correct? Can anyone tell me? Is it correct or incorrect? Is it correct? X equal to 0 is this line or what? What do you think?
I think it's correct. So
It's correct. Yes, Shravan and Aryanjali, is my diagram correct?
Yes, sir. I think so, sir.
Hmm?
I think so, sir. It's correct, sir.
What does x equal to 0 means? It means that no matter what is your coordinate in x,
It should
what
be
is
B.
your coordinate in y, x is same. This is not x equal
Same.
to 0, it is y equal to 0. What should be the line for x equal to 0? This line, na? If this is your y direction, if this is your x direction,
Yes,
this
sir.
means
I
what?
thought you were taking in different perspectives, sir. That
Acha,
you would
acha.
take the lower one. That's way.
Oh, okay, okay. Okay, that won't help because when I did this problem back as a student, I also faced the same problem. I also thought it that way, but it won't be helpful because we have to deal with vectors, okay? And vectors will have components in x, y, z direction. So now it looks okay. So what is the normal component? Normal to what? Normal to the interface. What is the normal component? Normal component. And see, there is no mention of free charges. That means free charges are absent. Sigma is 0. We can assume that. So normal component of D will be continuous. That is D2 n D1n. Now what is a D1? What is D1 vector? 2i cap, sorry, 12i cap, 10j cap, 4k cap. Isn't it? So what is the normal? What is the component normal to the surface? This one. Why? I cap means which direction? I cap means along the direction of x. Isn't it?
Yes, sir.
So what is the normal component? 12i cap. Remaining would be the what? Tangential components. So by continuity of tangential components of E, what we can write? E2 T equal to E1 T. But I don't have V, I have D in the question. So I'll do this. So what is the tangential component of uh, D2? Like this. What is epsilon 2? Vacuum. Vacuum has permittivity 1. Sorry, epsilon 0. This one has permittivity 2.5 times of that. What is the tangential component? The remaining part. So it would look like this. That is D2. D2 tangential. So what is overall D2 vector? How will it look like in the other medium? Understood?
So how did you relate that? So D2n equals to D1t, so
Oh, sorry, it's same. Thanks for
the same,
correcting.
sir.
Yeah. These are the normal components. Okay, that I can write it like this. I'm just denoting it by that.
So
And
can you
these are
explain that
the
why you
which one?
so that why you chose that part that way, sir, like x equals to 0, sir? Why not the previous one, sir?
Because here I have a vector given, na? So vectors are expressed in terms of this I, j, k. These are the directions in Cartesian coordinate: I cap, j cap, k cap. Okay, so I have to draw the picture keeping in mind the Cartesian coordinate system. I cap, j cap, k cap. No problem. You can call this one x, this one y, this one z. Doesn't matter. But if you draw like this, it would be difficult for us to comprehend because we're accustomed to call this direction x and this direction as y most of the times. Okay.
Yes, sir.
That's why I made this. Okay, if you had made like this, then you have to call this one as I cap,
Sure.
this direction.
So,
Yes, Shravan?
so like in that diagram, no, sir.
Hmm?
In the diagram, sir, I think you have wrote epsilon wrong, sir.
Oh, did I interchange? Let me see.
Like this should be like in the
Oh, yeah, yeah. It is 2.5,
left
no?
hand side. It should be like that should be the first medium. That should be the
It should
second
be first
medium.
medium.
Yes, sir. That should be the second medium. So in the answer it should be like 2.5 epsilon not
Beta.
by epsilon, right?
This is first medium, so it should be epsilon 0. And
How
this is
sir?
greater than. Now, is it correct?
No, sir. You wrote the correct thing like before, sir. In the first medium, it should be 2.5 epsilon naught, and this side only epsilon naught.
Oh, cha cha cha. First medium 2.5. Now,
Epsilon naught, and that's only and like in the like when we are doing b to
second medium.
t, when we are finding the value of b to t, it should be like 2.5 epsilon naught by epsilon, no, sir. A little bit below, sir.
2.5.
Yeah, yes, I. Out here
Is it?
you wrote E2 by E1 D1T.
Uh, so E2 is epsilon 2 is how
No,
much?
no.
Epsilon? No, it's okay.
Yes.
Yeah,
You
epsilon
wrote
2
the
is
right thing. You
epsilon
wrote it.
0.
Yes. You wrote the right thing. I just got confused. Yes.
It's correct, na?
Yes. Correct, sir.
Okay. Yeah, now we have to find theta 2. Very simple. So what did we get? We got that. Uh, how can we find theta 2? This D2. D2 looks like this. 12 I cap, 4 J cap, 1.6 K cap, and D2 cos theta 2 is what? It is the normal component that is equals to 2 I cap. Hmm. So cos theta 2 is what? I can write it like this. The magnitude. What is the magnitude of 12 I cap? It's only 12. What is the magnitude of D2 vector? This thing. So theta 2 would be cos inverse of this thing. Okay, it would come around 20, 19.75. Okay, you can try this at home.
Okay, sir.
Okay, understood. You can try
Yes,
the.
sir.
You can go to the internet. You can search for previous year questions of just then IIT JAM. There you can find these kind of questions. Okay. The main trick is to identify the normal and tangential components. And no problem. We would have done the problem like this as well. But you have to remember that then your I cap would be like this. Because when you will draw I cap, it may look like as a I cap is along y axis. That's why I chose it like this. No problem. You can draw it like this as well. Okay. Okay. So is anything left from this chapter, dielectric? Please tell me according to the syllabus. Please check.
So that capacitor, sir. Capacitor filled with
Capacitor.
dielectric.
Right, right, right. What is there in capacitor? Can you tell me the topics? Name of the topic?
The parallel plate, spherical and cylindrical,
Parallel but spherical, cylindrical. Okay, okay, okay. Okay.
filled
So
with dielectric.
and rest of the things
Fully
have
cap-
been done, na? Just check once.
yes, sir.
Okay, okay, fine.
Yes, sir.
That is an application of dielectrics, capacitors. Okay, so tomorrow we can do that. No problem.
Yes, sir.
Okay, okay. Thank you then, everyone.
Thank you, sir.